Hi y'all, I hope that you are doing well. This is the fourth lesson for our acids base. And what we're going to be talking about is how do we measure acids and bases. So this is kind of an introduction to the pH scale and what that is. So first thing is that acids and bases are measured on a pH scale. What we generally think of as a pH scale is a number of 1 to 14. That's the most common range for acids and bases. However, there are really strong acids and really strong bases that can go below 1 on the pH scale or over 14 on the pH scale. We have three kind of categories that we put these in. So when something has a pH of 7 or 6.5 to 7.5, we consider this neutral, which means that there's kind of an equal amount of hydrogen donation and hydrogen acceptors in the solution. Just like we've been talking about with the Bronsted-Lowry definition, where acids are proton donors and bases are proton acceptors. When a pH is less than 7, it's considered acidic. That means that there's more proton donation, more hydrogen ion donation in the solution than there is acceptance. And then a pH of greater than 7 or 7.5 is considered basic, which means that there is more acceptance of hydrogen than there is donation of it. So what we can do is we can actually use this pH scale, which I've put over here. Oops, let's start my pen so you all can see what I am writing. I'm going to use purple today. So what we can see here is that this is our pH scale. So you will often see this. This one actually gives you some different values. It shows you some things that we use every day. Ammonia you've probably heard of, blood, water, milk, vinegar, lemon juice, stomach acid, right? I saw lots of you mention that stomach acid is acidic, which is true, so that is there. And what we can do is we can use this scale to look at what different pH values are, right? So this first one we have over here is a pH of 4. So all we're going to do is you can see that there are numbers here along the side, so I can find this pH of 4. And if I look over on this left-hand side, I can see that this is actually in the acidic section, very clearly the acidic section. And so what I can write here is for this pH of 4, I can put acidic, right? I can do the same thing with pH 11. It's in the basic section. And then a pH of 7, which is right here in the middle of neutral. So we are just going to write neutral. Oftentimes we think of these pHs as whole numbers, 4, 11, 7, but we can have decimal points. We're going to figure out how we get those decimal points in just a little bit, but let's look here that if I have a pH of 8.9, that is between 8 and 9, which again puts me in a basic category. If I have a 5.6, we're between 5 and 6, which is an acidic category. And then my 7.2 is kind of in between that 7 and 8, which is really kind of in this kind of happy neutral spot right here between 6.5 and 7.5, so I'm going to put neutral. Right, so this is going to be the first part of your worksheet, is something very similar to this, where you are going to be determining whether things are acidic or basic or neutral. So when we measure pH of a substance, right, so we have all of these values, but how do we actually measure that in a liquid, right? So there's a couple of different ways. You might have seen these guys around the classroom with my IB students. So these are just little strips of paper that you can dip into a solution, and it's going to tell you what the pH is. Another thing we can do are indicators colors, right? So these are solutions you add to a liquid, and it tells you what the pH of it is. You'll notice that some indicators, like this universal indicator, changes color over the entire pH scale. Whereas other ones, such as phenolphthalein, this second one, is really good at determining neutral to basic solutions, but it would not be good to use for an acidic to basic solution because it would just, or an acidic to neutral solution, because it would stay as a clear solution the whole time. It doesn't give us a lot of information. The last one that I want to point out here is the bromothiamyl blue. So this is also called BTB, right? So when you all with last year lit ethanol on fire, you started with this blue BTB, this basic BTB, and what happened is we saw an increase and we started getting colors like this. So we saw that there was an increase in acid, so an increase in your hydrogen donation into the solution, and it changed colors for us. The last thing we can do is with these fancy meters over here. They have meters, they're digital meters that you can use with predetermined solutions that we know the concentration of. And that allows us to determine what the pH is. And this pH scale over here, this is another one. It gives you some more examples of things that you know of and you have interacted with to tell you kind of what these different things are. So we can also calculate the pH. pH is measured on the negative log of the concentration of hydrogen ions that are given off. It sounds really complicated, but really it's just a math equation that tells us that pH is equal to the negative log of H positive ions. Concentration of H positive. These little brackets here mean concentration. The pH is in an aqueous solution, so remember that is where everything is dissolved in water. And if I take the pH and the pOH and combine them, they're going to equal 14, right? So pH plus pOH is equal to 14. This is one of our key equations, as is this one. And then you can also figure out pOH. So it's the same process as our pH equation, except for we're going to use a concentration of pOH, right? Sometimes, though, we are not going to have the concentration of hydrogen ions. You're going to be taking the pH, so you're going to get a pH value, and then you're asked to find the concentration of hydrogen ions. And all we do is mathematically we rearrange this log equation to get the H plus is equal to 10 to the negative pH that you are given. So let's see what this looks like with some problems. We're going to do 5 problems together, and then you can come back and refer to these as you're doing your worksheet. So, problem number 1. What is the pH of a solution with a hydrogen ion concentration of 0.25 molar, right? So we know that the equation we're going to be using is that pH is equal to the negative log of the concentration of the hydrogen ion. And right now, this is my hydrogen ion concentration. You can see that it tells me this right here. So pH is equal to the negative log of 0.250 molar, right? Remember this little guy? Molar, that's our concentration in a solution. So if I plug this in to my calculator, my computer calculator or phone calculator, making sure I put this in the right order, I should get 0.60 as my pH. And there is no units on pH. So y'all are lucky. You're not going to lose any points for forgetting your units because there are none. So that's our first example. The second one, very similar. What is the pH of a solution with a hydrogen ion concentration of 1.25 times 10 to the negative 4 molar? So I'm going to write our starting equation again. pH is equal to the negative log of the concentration of the hydrogen ions. So again, we're looking for the pH, right? What is the pH? We know we have the negative log, and our concentration is 1.25 times 10 to the negative 4, right? So a smaller value than before. And this tells us, if we do the calculations, that our pH is going to be equal to, I apologize, I'm getting a phone call. Our pH is equal to 3.90, right? So the smaller the concentration of our hydrogen ion, the higher the pH value is going to be. Okay, so this one gets a little more complicated, right? So this hydroxide ion, right? So I don't have my hydrogen ion concentration. I have my hydroxide, but we can still solve this, right? So instead of solving for pH, we're going to solve for pOH. Remember, that equation is the same, negative log of the concentration of OH, right? So just a couple of changes. So we're going to do the same thing as before. We're going to get the negative log of our OH concentration, which is 0.250. So my pOH, because this is the same problem we did in the beginning, is going to be 0.60. However, I'm looking for the pH of the solution. So what I need to do is remember that pOH, so this is that second equation I said is going to be important, is equal to pH, adding the pH, to 14, right? So we're just going to plug in our values. This 0.6 is equal to our pOH, so we got 0.6 plus pH, which is what we're looking for, is equal to 14. I'm going to subtract 0.6 from each side. And then my final answer, my pH, is going to be 13.4. Oops, 13.5, because we're just going to do the subtraction. All right, so oftentimes, right, I talked about the fact that sometimes you will have to calculate the pH, but sometimes you're already going to be given the pH, right? So in this situation, we have what is the concentration of hydrogen ions if I have a pH of 13.2? So we know this equation, pH is equal to the negative log of the hydrogen concentration. This can be rewritten so that we can have the hydrogen concentration, this part, all by itself. And what that looks like is we have H plus is equal to 10, because that's the base of our log, to the negative pH. Right? So in this case, our hydrogen concentration is going to be equal to 10 to the negative. This value up here, this 13.2, is my pH. 13.2. Right? So if we plug all that in, my H plus concentration is going to be equal to 6.3 times 10 to the negative 14th. Right? So we get a really small number because we have a really high pH. All right. Final practice problem, and we're just doing the same thing, right? So pH is equal to the negative log of the concentration of hydrogen. Again, we have this pH value because we're looking for the concentration of hydrogen. So we're going to rewrite this where H positive is equal to 10 to the negative pH. So my H positive is equal to 10 to the negative 2.7. Right? When I plug that in on my calculator, right, I'm going to get 0.002 moles, or I can write this in scientific notation, 2.0 times 10 to the negative 3 moles. And the way we do that is I go 1, 2, 3. I moved it over 3 decimal places, and I moved it to the right, so I put in this negative 3 up here. So you're going to practice those on your assignment today that I'm going to upload. And then I just wanted to go over a real quick definition, right? So we are using the Bronsted-Lowry definition of acids and bases. We talked about the Arrhenius and the Lewis. The Arrhenius was an idea before Bronsted-Lowry, and the Lewis acids is the most accurate definition, but really what we're looking at is fine with the Bronsted-Lowry, and it's a little bit easier, so we're going to continue to use that. Acids donate protons. They donate those hydrogen ions. If you ever eat an acid, it's sour. Think about lemon juice, right? Or an orange that's maybe not quite ripe. If you spill it on yourself, it can burn or it can itch. That's why they're called acid burns. The pH is 1 to about 6.5. Remember, we really talked about that 7 being neutral. And when they're dissolved, they can, in fact, conduct electricity. Bases accept protons, right? They accept the proton, usually from an acid. They're bitter. If you ever eat one, they're bitter. We can see milk go bad, and that tastes a little bitter. They feel slippery, so soapy water is a great example, or ammonia, if you've ever cleaned with that, kind of a slippery feeling. And then remember we talked about here, 7.5 to 14 is really our values. That 6.5 to 7.5 is kind of neutral, and they also conduct electricity. So hopefully this is a little helpful. You can review this as many times as you need, but please do the worksheet, and good luck. Let me know if you have any questions.